In the last lecture, we introduced you to what is known as Einstein, Podolsky and Rosen paradox, in short the EPR paradox. And just to take you back to the last lecture, we said the Einstein insisted that an object must possess a property independent of the process of measurement, while the quantum mechanics said that it is during a measurement that the particle acquires a property. There were two elements, one was realism and the second one is locality. So we said that a measurement on a part of a system, for instance in our case the entangled pair, cannot influence the property of another system, another subsystem, if they are well separated physically. And Einstein demands that any acceptable physical theory must satisfy the requirement of this dual property of locality and realism. We then introduced a version due to David Bohm, which talked about a particle of spin 0 disintegrating into two spin-half particles. And then of course, because of conservation of angular momentum, the state of the particle must be that of a singlet, and that is given by 1 over square root of 2 up down minus down up, which is another way of writing down 0 1 minus 1 0 in our cubic notation. Then we said that if Bob is to measure the particle also along z direction, if Alice had measured her particle, that is particle number 1 along z direction, and got Sz is equal to h cross by 2, Bob is guaranteed to get Sz equal to minus h cross by 2. That's a down state. In other words, there is perfect anti-correlation between Alice's measurement and Bob's measurement, even though the two are measuring on two different particles. Now let's look at what happens if Bob, instead of measuring along the z direction, decides to make a measurement along an arbitrary angle theta with the z axis, the usual theta phi coordinate in the spherical coordinate system. So we have an n, arbitrary direction n, which is given by the Cartesian component sin theta cos phi, sin theta sin phi, and cos theta. Now we will show that though the anti-correlation that exists now is not perfect, in the sense if Alice got +1, Bob would get -1 and vice versa, there is still some correlation between the two measurements. And in order to do that, recall that if Bob's measurement is taken along the arbitrary n direction, then the eigenstate of sigma n having an eigenvalue +1 is given by, as we wrote down, e to the power I phi by 2 cos theta by 2 into e to the power minus I phi by 2. This is a symmetric way of writing, and we will always ignore this overall global factor, sin theta by 2 e to the power I phi by 2, and the eigenvector corresponding to -1 eigenvalue is given by e to the power I phi by 2 sin theta by 2 e to the power minus I phi by 2 and minus cos theta by 2 e to the power I phi by 2. Now notice, my sigma z, if I am looking at the eigenvalue of sigma z corresponding to z equal to -1, sigma z is the eigenvalue corresponding to -1 along the z direction. Let me indicate it by like this. Now that is, we have seen is 0 1 state. Now since we said that if Bob had to measure it is along the z direction, he would get -1. So he would get this state. Now you can, it's a trivial algebra to show that this happens to be sin theta by 2 n plus minus cos theta by 2 n minus. Now you can immediately see what it tells me. That is, Bob will measure the Sz equal to minus h cross by 2 with the probability cos square theta by 2. So in other words, the measurements are still correlated, though there is no perfect anti-correlation, as would be the case if Bob were to make his measurement also along the z direction. So we had seen the conflicting point of view, which is summarized in this slide, but since I had discussed it earlier, I am not going to go through it. Now we said that Bells made a gedanken experiment, and for that, let us consider the same state. Only thing is, I will not write as up down minus down up, but I will write this as the state psi minus one of the 4 Bell states, which is equal to 1 over square root of 2, 0 1 minus 1 0. Now I proved it last time that if Alice is to make a measurement on particle number 1 and Bob is to make a measurement on particle number 2, then as long as they make a measurement along the same direction, it doesn't have to be z direction, along any direction, then this quantity sigma IA plus sigma IB acting on the state psi gives me 0. Which means that sigma IA acting on psi is the same as minus of sigma IB acting on psi. Now what does it actually mean? It means that if I have an operator sigma IB which is acting on particle number 2, I can equivalently replace it with minus sigma IA on particle number 1, and that is what is shown in this slide. Now let us look at this quantity. So we are looking at what is the expectation value of psi in the state psi. If Alice is to make her measurement along an arbitrary direction A, let us call it sigma A dot A is the unit vector, and Bob is to make his measurement along an unit vector direction B, psi, what is this quantity? Now according to what we said just now, this is equal to, I can replace this sigma B which is acting on particle number 2 with a minus sigma A, but then sigma A always acts on particle number 1. So this is equal to minus of psi sigma A dot A sigma A dot B. So I don't refer to Bob any longer. Now expressing the dot products, I get this as sum over ij psi sigma ai sigma aj psi, and of course multiplied with ai bj. This is my the quantity that I get. Now let us actually take a bit of a time in calculating this quantity. What is this? But first, there are several terms here, but let me try to see, to be precise, there are 9 terms here. Let me see what are the off diagonal components, namely terms for which I is not equal to j. So for terms I not equal to j, there are 6 terms there. Now I would like to group them into 2 pairs of 3 terms each. So let me look at the following quantity: sigma xa, sigma ya plus sigma xb, sigma yb, sorry, this is sigma y, let me cut this out, sigma xa, sigma ya plus sigma xa, sigma za plus sigma ya, sigma z. All of them refer to A because we have replaced it with a minus sign. Now let us look at this calculation, not all that time consuming calculation. So this is minus. So I had 0 1 minus 1 0, this is the bra, and so let us take this term. So I get sigma xa, sigma ya acting on 0 1 minus 1 0 plus the same bra sigma xa, sigma za, just written it down, there is nothing being done other than routine algebra. Now look at that. Remember what sigma x does. Sigma x simply manages to flip 0 to 1 and 1 to 0. Sigma y does essentially the same. So, but sigma y acting on a 0, sigma y acting on a 0 gives you I times 1, there is a phase factor there, and sigma y acting on a 1, you have to be careful, it is minus I times 0. Now that tells me that this term that is there, so notice what is happening here. Sigma y, remember all of them are acting on the first particle, and I have to put them in the order in which they appear. So in this case, this sigma ya acting on 0 gives me I times 1, sigma x flips it back. So therefore, other than for the state flipping from 0 to 1 back to 0, I have simply collected a factor I. Now let us look at this. Here also the same thing happens. So look at what am I getting here. So I get again the sigma ya acting on this state, and so this will give me, minus sign is already there, 0 1 minus 1 0 into, as we said, I times 0 1 plus, because that was a minus I, 1 0. Okay. Now look at what this actually is. This state 0 1 is of course the same as this state 0 1, so I get a factor I. But 1 0 is orthogonal to 0 1, so I get 0. But this state is the same as this state, but there is a minus sign here, so I get a minus I. So I minus I get 0. Now these states are much more straightforward. In this case, so this is, I will write down the second and the third term earlier. So this term, as we have seen, is I minus I, so that's equal to 0. Now if you look at this term, sigma z acting on 0 does nothing to it, but sigma x acting on 0 after that changes the 0 to 1. So instead of 0 1, I will have a 1 1. Now similar is the situation here. sigma z acting on 1 gives me minus 1, so this minus sign will become plus sign. But then sigma x acting on that 1 will give me 0. So the state that I will get here will be 1, 1 minus 0, 0, which is of course orthogonal to this state. So therefore I have my second term as 0. The third term similarly gives you 0 because it's very similar to this term where I got 0, 0 plus 1, 1. Here also I will get very similar thing, but because it is not, it's an y operator rather than x operator, there would be some i's coming in, but nevertheless the resulting term will be orthogonal to this term. So therefore this will also be 0. So the result is 0. Now this is what happens to the non-diagonal term. There are 3 more terms, but then it doesn't matter because there will be sigma ya, sigma xa, sigma ya, sigma za, sigma za, sigma ya, and identically those 3 terms will also turn out to be 0. So what am I left with? I am left with only the diagonal terms. So I have psi, I get ai bi because only I is equal to j term. I have a sum of course over I. Then sigma ia, sigma ia again, psi. Minus sign has taken care of the fact that there was a sigma ib there, but I now have written it as sigma ia. But you see sigma I square is equal to 1. So therefore this quantity is minus sum over I, ai bi, psi, and of course the state psi is normalized. So therefore I have this as minus a dot b, and which we have said is nothing but minus cos theta, because Bob is making a measurement along an axis which is making an angle theta with that of Alice's axis. So you notice again we have reiterated using explicit calculation that if Alice is to make a measurement along one direction A and Bob is to make a measurement along a second direction which is B, then their results of Bob making that measurement of his spin, Alice making a measurement of her spin, is given by what is cos theta. So there is still a correlation. Now it is this correlation that we will consider in the further discussion of what it means in terms of quantum mechanics. Now this slide simply reminds you, which I have talked about a few minutes back, that the eigenstates of Pauli operator along an arbitrary direction n are given by these matrices. Now suppose Alice is making a measurement along a particular direction and gets a particular value, supposing she gets a plus. Now what am I actually doing? I am projecting out the n equal to, if she gets plus 1, I am projecting out the eigenstate n having an eigenvalue plus. Now you can check it immediately, which I will indicate how it is done, that this quantity, half of I plus n dot sigma, is a projection operator for the state n plus, and identically half of identity operator minus n dot sigma is the projection operator for the state minus. Now this is easy to work out, but let us do this. I will briefly do this algebra for one of the relations and then I will sort of urge you to do the calculation for the others and see that that's correct. So suppose we are saying I plus n dot sigma acting divided by 2 of course, acting on let us say up state. This is z equal to plus 1, sigma z eigenvalue plus 1. So what does it give me? So since this is an I get simply half 1 0 plus. Let us expand this out. So I have nx sigma x plus ny sigma y plus nz sigma z acting on the same state 1 0. Now what do I get here? So firstly let me keep this nx operator as it is, sigma x nx direction as it is, the component Cartesian direction. Sigma x operating on 1 0, I know just inverts it, that is flips the qubit. Then I have half ny. Now sigma y acting on 1 0 also flips it, but there is a factor of I there. And as before, sigma z does nothing, so therefore it is 1 0. Now remember, this term will pick up a minus sign if it were to act on the 0 1 state. Now let us write it as a single matrix. So look at what am I having. I have a half there. I have 1. Now recall that my nx is sin theta cos phi, ny is sin theta sin phi, and nz is cos theta. So I have got 1 and only a term coming from nz, so it is 1 plus cos theta. The other element is there is nothing from here. There is a nx here, so let me write it as sin theta cos phi plus this is I times sin theta sin phi. But then this is equal to 1 plus cos theta. If you take sin theta common here, I get cos phi plus I sin phi, which is nothing but e to the power I phi, which is other than for a global factor, which I can pull out a e to the power I phi by 2. So which is, remember that 1 plus cos theta by 2 is cos square theta by 2. So this is, if I pull out a e to the power I phi by 2, I have cos square theta by 2 e to the power minus I phi by 2, and this is, I have got sin theta divided by 2. So if I write down here sin theta, now remember sin theta, there is a half there, so let me keep that sin theta by 2. Remember that sin theta can be written as 2 sin theta by 2 into cos theta by 2, so that this 2 and that 2 will cancel out, and I will be pulling out a factor cos theta by 2, and I will be left with a cos theta by 2. This is shown in the slide, cos theta by 2 e to the power I phi by 2, which I have taken out, and the remaining thing which is there is nothing but the eigenstate along n direction with an eigenvalue plus. The remaining relationship are also as shown there. So what we have shown is that I plus n dot sigma by 2 is a projection operator for the state n with an eigenvalue plus. And this acting on, for example, the state 1, 0 we have shown, it gives me cosine theta by 2 times e to the power I phi by 2, an immaterial phase factor, and n plus. The slide shows the other possibilities, that what happens when the same operator acts on the state sigma z equal to -1, you find that it gives you essentially the same state but with a factor sine of theta by 2, and 1 minus n dot sigma by 2 is the projection operator for the eigenstate n minus, and acting on state -1 gives you this, and that is as written in the slide. But then let us look at what this quantity gives me. Alice makes a measurement along the axis A using this operator, Bob along some direction m, also plus psi. Now look at this, since this psi is 1 over square root of 2, which we retain as it is, and so let me rewrite this, n plus pb m plus acting on 0, 1 minus 1, 0. Use the four relations that I have shown in the slide. So this is giving me 1 over square root of 2. Now let us suppose the direction n makes an angle theta 1 with the z axis, and the direction m makes an angle theta 2 with the z axis. In that case, I get the following. Since this is acting on 0, I get cosine theta 1 by 2. There is of course e to the power I phi by 2 there. And this one, because this is B, it's acting on 1. So you get sine theta 2 by 2, because this is direction m, into e to the power minus I phi by 2. And what this is projecting is n plus and m plus minus identical way. This is because it's acting on 1, so I get a sine theta 1 by 2. The exponential factors will cancel out as in the first term, and I get cosine theta 2 by 2, and this is again giving me the same n plus and m plus, because the projection operator used in both cases is the same. So that's equal to 1 over square root of 2 sine of theta 2 minus theta 1 by 2 n plus m plus. And if the angle between the two axes is theta, this is simply equal to 1 over square root of 2 sine theta by 2 n plus m plus. Now I can do the same calculation for the other 3 projection operators and get results which are tabulated in these slides. So therefore, if we now decide that Alice and Bob decide to make their measurement along direction n and m respectively, then we can calculate what is the expectation value of, let us say, PAN plus PBM plus. Remember that all that I need to calculate this is to realize the projection operator squares are projection operators themselves. So I can write this PA as PA square, PB as PB square, and I can make one pair act on the ket, one pair act on the brother, and get these relations as have been written down. So you notice that when they get PA plus plus, that is PA plus PB also gives me plus, or minus minus, my probability is half sine square theta by 2, and when they are dissimilar it happens to be cos square theta by 2. Now what is suggested now is, we have not said what these directions are. Let me choose direction n1 to be the z-axis, n2 to be a direction which is in the fourth quadrant, making an angle of 30 degrees with the positive x-axis, and n3 is in the second quadrant, making an angle of 30 degrees with the z-axis. The respective unit vectors are written down there. Now what happens is this: Bohm measures the spin of his particle along n1 direction. Actually what Bob would do is to measure it really along minus n1 direction, so that Alice doesn't have to worry about changing that minus sign. Bob would make the measurement along minus 1 direction, communicate it to Alice. Now you see, once Alice makes a measurement on her particle along n2 direction, C is no longer able to find out what her result would have been had she made a measurement along the n1 direction. But Bob's information lets her know that. So therefore, Alice can have the information about the result that she would get on a pair of direction at the same time, n1 n2, n1 n3 and n2 n3. So what she does is the same, that looks at that for a given pair of axes, does she get the same result? By same I mean, does she get plus plus or minus minus? So concentrating on only the same results, the probabilities would be, because there are two possible results, so 2 into half sine square theta by 2, and that works out to be equal to 1/4 because of the choice of the angles that we have taken, because sine theta is 1/2 for 30 degrees. Now with this, we conclude that if she only concentrates on get the probabilities of having the same result when she does measurements along n1 n2, n2 n3 or n1 n3, and sums up the probabilities for the same result, the result must be equal to 3/4, which is less than 1. Now what happens if there were hidden variables in the problem? Now local realism doesn't give any anti-correlation between Bob's and Alice's result. So therefore, Bob's informing Alice that this is the result I got, it is totally imaginary. But then Alice can make the measurement along the two axes, because there is no collapse of the waveform. Now, so therefore we recalculate P same for n1 n2, n2 n3 and n3 n1. But remember, I have only 3 possible results. Plus, I can have a plus plus, minus minus, or plus minus and minus plus. Whatever happens, one of those results is guaranteed to give me the same, because it could be plus plus or minus minus. I don't care. We could have plus plus, plus minus minus plus, or minus minus, plus minus minus plus. This is the worst situation. But then one of those events has a probability of 1. And then this tells me that the probability of the same result is greater than or equal to 1, because at least one of them terms is 1. So this provides a test for which one is right. One of them says it is less than 1, the other one says it is greater than or equal to 1. And if hidden variable theory is correct, you should get greater than or equal to 1. If quantum mechanics is correct, you should get less than 1. And that is what will determine, if one can do this experimentally, That is what would determine whether quantum mechanics is correct or the hidden variable theory is correct.